the guy who organized this week, it falls on me as well to say a few introductory words. Welcome. I think that's as few as possible, but sincerely from Peter Cameron, Bill Jackson, Alex Scott, Alan Soto, and myself. We're all very pleased that you could join us for a week or a month or a semester, however long you can make it. And personally, I know that I am looking forward to talking with a lot of you and learning a lot from you over the course of these months. I think the connections between combinatorics and statistical mechanics are extremely interesting, and I suppose you do too, or even if those of you here. So I think it's going to be a very fruitful venue for a lot of interesting conversations and collaboration. So without further ado, our first speaker is Bill Jackson. He'll give us an overview of graph theory.
Yes, so I think it's just trying to give an overview of graph theory, I think, is very difficult. It's such a mixed audience. So I think a lot of people will know just about everything that I say. So what I'm trying to do is to set up a kind of common playing field so that everybody has at least some idea of the basics of graph theory. One thing about graph theory is I think everybody has different terminology and notation. So one idea will be for this talk to try and fix notation, but as soon as I finish, everybody will adopt their own notation anyway. So I thought I'd start at the beginning to say what a graph is. So I'd like people to take part. So I like people to shout out that there is at least one mistake in these slides, so that the person who finds the mistake gets a pint of beer or an equivalent drink. So a graph is two disjoint sets and an incidence relation between them, which associates a pair of not necessarily distinct vertices with each edge. So I allow the pair of vertices incident to an edge to be the same, in which case the edge is a loop, and I allow different edges to be incident with the same pair of vertices, so we can have multiple edges. So a graph's simple if it has no loops and no multiple edges, and it's finite if both sets are finite. So all the graphs that I'm talking about, I'm going to show from now on that all my graphs are finite. And here's two basic graph operations. So if we have a graph, we can delete an edge from a graph. So it just gets deleted from the set of edges. We can delete a vertex from a graph. So if we delete the vertex, then we delete all edges which are incident to the vertex. Contraction is it's a bit more complicated to define for graphs, which is, so when we contract an edge, I guess one way of describing it is we delete its end vertices and add a new vertex. So if this is my edge A and this is J, then J contract A, I'm going to get what I call my vertices. Was it V and W? So I'm going to delete V and W and add a new vertex. I call it Z. Oh yeah. Oh, sorry. Let's put it on top of W. So we call this Z. And this edge is incident with the new vertex Z. So this is what I mean by the contraction operation. If we're working with simple graphs, then in some, it's quite normal to delete parallel edges after you do it with contraction. But most of my graphs are not going to be simple, and I'm going to retain multiple edges when I do contractions.
So another way of saying it is you first delete E, and then you contract V to W.
Yeah, but I don't want to contract non-adjacent vertices.
Because if you wanted, you could simply define contraction of a pair of vertices.
Yeah, yeah, but I'm not going. I'm not.
That's not contraction. That's a different operation.
Or identification.
Yeah,
Yeah.
yeah.
So just a note that if we have a loop, then deletion is the same as contraction. Can you say at the back, because it looks quite faint here?
It's okay.
Yeah. I could try and turn these lights off.
Mainly because this thing is at half power at the moment.
Ah,
That's the problem.
so it'll
It needs to be, I don't know whether it's another lamp or what it is, but that's the best we can do at the moment. I'm sorry.
Okay.
I hope it's okay.
yeah. Well, it's okay for me. I hope.
It's okay, yeah.
Good.
Turn off the safety policy, that helps a bit.
Turn off the safety policy. Good. So if anything happens, it's Gordon. So a subgraph of a graph is anything we can get by recursively deleting edges and vertices, I guess. Isolated vertices is not really relevant. I mean, we can make a vertex isolated by deleting all the edges instantly. A contraction of a graph is anything we can get recursively by contracting edges. And a minor of a graph is any graph which we can get recursively by these two operations. So deleting or contraction edges and deleting isolated vertices. So the nice thing about graph theory is you can state very deep theorems simply. So this is a very deep theorem, but after 3 slides I can state it to you. So it's
I just have a question.
yeah.
Is a graph plus an isolated vertex the same minor as a graph without that isolated vertex? Trivially, if you have a single edge, and first you delete the edge, you get a minor that consists of 2 isolated vertices.
Mm-hmm.
Is the graph you obtain by deleting one of them different as a minor? Is it a different minor from? I think it is.
Could you run one slide back so we can see
Okay.
what the definitions are?
In other words, is the graph labeled?
The vertices.
The vertex, either way.
Sometimes.
I think very clearly, minor, sorry, defined by 3 operators also include removing isolated vertices.
Yeah, I think I'm already
So I
removing.
think it's correct.
Right, but removing isolated vertices is optional, right? You can take them out or not
Okay.
take
Yeah.
them out.
Okay.
Yeah.
Okay.
Right.
Yeah, so it should be
All right.
correct.
So you don't have to remove
You don't have to remove
Yes.
them. And the answer to the labeled question is sometimes you will treat isomorphic graphs as identical and sometimes you won't.
Yes.
And you will, without warning, switch back and forth between the 2 points of view.
So, for example, I guess this is unlabeled graphs, because we could just put lots of silly labels on and it would not be true. So this this was a theorem of Wagner in the 30s and proved by Robertson Seymour, I guess, in the 80s. So it was Wagner's quasi-well-ordering conjecture. So it says that if we have any infinite sequence of graphs, then some graph in the sequence is a minor of one of the later graphs in the sequence.
The total proof of the complete proof of this theorem took how many pages, approximately?
Or how many? Well, it's over 20 papers, I think. Is it, Jeff?
25, I think. I think the proof's just come out, hasn't it? That the graph minus 25.
No, it's 20.
20, is it?
But
Oh,
they're not all part of the proof, but most of them are.
Yeah.
But some of them are proof of doing algorithms.
Depends on letter size.
So there is a lot more in the proof. So it's created a whole theory of graph minors. So it has this important corollary that if we have a minor closed family of graphs, such as a graph embedded on a surface, then there is a finite set of excluded minors. So a graph belongs to the minor closed family if and only if it. So there is a finite set H. Let's try this. Yeah. Oh, there we go. If we have a minor closed family of graphs F, then there's a finite set of graphs H, such that any graph G, we can test whether G belongs to F by testing whether it has a minor, it has one of these finite set of minors. So the corollary follows easily from the theorem because we let H be the set. Well, it's a set of all graphs G, such that G it's a set of minor minimal graphs which do not belong to F. So G is not in F, and G minus E and is in F, and G contract E is in F for all E which are edges of G. So this is the set of graphs with the property that they do not belong to F, but every minor of them does belong to F.
I guess you probably also want to say G has no isolated vertices.
No, those would be minor. They have minors that.
Yeah, there wouldn't be minor minimal if.
Yeah, but he didn't write that because you didn't also write about deleting isolated vertices.
No, I did in the minor
Oh, I see.
operation, didn't I?
But not there.
Oh yeah, sorry, not there. No. Isolated vertices are a pain. I guess matroids are much nicer, Jeff. So by this definition, no two graphs in H can be a minor. If you take two graphs in H, then one cannot be a minor of the other, because if we have G1 and G2 in H, then neither G1 nor G2 belong to F. So, because they're minor minimal, no graph in F can be a minor of another graph in F. So by the Robertson-Seymour theorem, this set H is finite. So as part of the graph minor theory, they also give a polynomial algorithm for checking whether a fixed graph H is a minor, a fixed graph G1 is a minor of another graph G2. So this gives us a polynomial algorithm for checking whether a graph belongs to any minor closed family of graphs.
If you know H.
Yeah, when I say it gives us, it means it tells us there exists a polynomial algorithm. There's a trick in that the multiplicative constants in the theory are astronomical. So the bound on the number of graphs in this set H is very, very large.
Did you say graphs on the surface are an example?
Yes, I'll come. Yes.
What would be H?
No, it's a good question. I'll actually come to that later. But
Okay.
I think so for the plane, then it's Kuratowski's theorem. So the graphs are K33. So the complete bipartite graph K33 and the complete graph K5. So I think the finite set of excluded minors is known for the projective plane. And do you know how many there are?
35.
So there are 35 graphs for the projective plane. I think the last time I checked it was not known for the torus. But I think the cubic excluded minors are known for the torus, and there are about 1,000 of them. Is that correct? So two operations, which I kind of guess have got an interpretation in electrical networks, are parallel extension and parallel reduction, and series extension and series reduction. So if this is my graph, then a parallel extension on this edge E is we replace E by another edge which is the same n vertices as E. So this is a parallel extension, and it's probably going the wrong way around, is it? Oh no. No. Yeah, so this will be H, and this will be J. No?
Yeah.
Good. And then series extension, we subdivide an edge. So to go backwards, if we have a vertex of degree 2 and we contract an edge incident to a vertex of degree 2, we get a series reduction. And if we have a cycle of length 2 and we delete one of the edges in the cycle of length 2, we get a parallel reduction. And sorry, if we can get if we can get a graph H from a graph J by a sequence of series reductions, then we say J is a subdivision of H. So subdivisions, we're allowed to put more vertices of degree 2. Yeah. Or we could say that J is homeomorphic to H. So we have unions and intersections of graphs, which are what you would expect them to be. We just take if we have a graph and two subgraphs, then the unions is just the unions of the vertex set and the edge set. And the intersection is just the intersections of the vertex sets and the edge sets. So that was kind of operations on graphs. So now I thought I'd start off on, there are some families of graphs. Oh, sorry. So a forest is a graph with no cycles. A tree is a connected forest. G is a series parallel graph if we can get G from, now I'm not sure about this, is it K2 or is it the cycle of length 2?
Or is it any tree, or is it any forest?
Depends.
Yeah, it depends.
Well, where you want to start.
Yeah, so it depends where you want to start. So I've decided to start at K2, but that's going to create a problem.
Maybe also a loop.
A loop? Yeah. So forests are minor closed. So any minor of a forest is a forest. So by the Robertson-Seymour theorem, there is a finite set of minimal excluded minors, and the minimal excluded minor is clearly just a loop. If we have a series parallel graph, then it has an excluded minor, which is the complete graph on 4 vertices. So you missed your opportunity to get a drink. So there's something wrong with this I discovered this at 12 o'clock last night when I was reading my notes, which wasn't the best precursor for going to sleep. But there's something wrong with this. So if this is the definition of serial parallel graphs, then this statement is not true.
Yeah.
So for example, if we take a tree with 1 vertex of degree 3, then this does not have K4 as a minor, clearly. And by this definition, it's not series parallel either.
Well, that's why if you want, I mean, I think your definition will give you all 2 connected series parallel graphs.
Yeah, that's what I
Like
thought.
that.
That's what I decided about 1 or 2 o'clock in the morning.
So if you want all connected series parallel graphs, maybe you should start from a tree rather than K2. And if you want all series parallel graphs, maybe you should start from a forest rather than K2.
Yeah.
And maybe you should allow tacking on loops.
Yeah.
Well, let's say another starting point that the series parallel network is constructed with a distinguished edge.
Yeah.
But there's a theorem that a series parallel network with a distinguished edge E1 and a series if you distinguish a different edge, the resulting graph is a series parallel extension with that other distinguished edge. So that it doesn't matter which distinguished edge you pick. But then you could start with a distinguished edge of that's a loop.
Yeah. I mean, I wanted to have K4 as an excluded minor in the statement, and I'd like the statement to be true if possible. So I thought maybe this is a true statement, but
I think K4 minus 3 means the up plane of graph.
sorry.
K4 minus 3 means up the plane of graph.
No, we'll get to that on the next slide, I think, but I think that's not true. So let's define series parallel. So this is, I mean, one problem is that this definition of series parallel is not a minor closed family. So it cannot be characterized just by an excluded minor.
Bill, why don't you just say, instead of starting with K2, start with an arbitrary forest.
Well, I
and
might
also allow adding loops.
yeah. Well, how about this? So series parallel, I'm going to start with a cycle of length 2. So I'm starting with this graph. And then all the graphs that I can get from this graph by parallel and series extension are going to be 2 connected. So we'll get to 2 connected eventually, but 2 connected means if you delete any vertex, it stays connected. So here's my guess. So J is a loopless. No. G is series parallel if and only if J is loopless, 2 connected, and does not have K4 as a minor. This isn't aware, is it?
If it's too connected, why do you need a loop in it?
Sorry?
If there's a loop there, it cannot be too connected.
Yeah. So My definition of toe connected was that if you delete a vertex, it stays connected. So in that case, loops would be allowed, but I agree with you, I would not want a toe connected graph to have a lobe.
Is a graph with no vertices connected?
Yes.
No.
No. Wrong answer. Why not?
Well, there are good reasons. You want a graph to be uniquely the disjoint union of its connected components. So if you allow empty graphs connected, you lose that unique decomposition.
The connected graph has to have one connected component.
Yes. That's the reason.
It's another, yeah.
So there's a paper by Harari, called "Is the Null Graph a Pointless Concept?"
Still kind of
Maybe you're referring to that.
Bill, I fear we're risking convincing the physicist that graph theory is a little bit like law or theology.
Let's move on. So we have graphs on surfaces. So we've already talked about this. So I didn't really want to define formally what an embedding of a graph on a surface is. So it's a drawing in which I guess the edges are represented by curves joining their end vertices. The vertices are represented by points, and we want the curves only intersect at common end vertices. So it's planar if it can be embedded in the plane. It's outer planar if it can be embedded in the plane in such a way that all vertices lie in the same face. So my standard graph is outer planar. And well, we've already touched on the Robertson-Seymour theorem.
So what is phase?
Phase is
Convex polygon, or?
well, it's some. If we delete the vertices and the edges, it's a connected region that is left.
Yeah, it's just a connected component of the surface minus the edges and vertices.
It might
Some
not
open
be
set.
simply connected. Do you allow the multi-connected region? The face can be okay. Can be a torus. Say that. Okay.
You probably
Is it?
you want to assume that the graph is embedded in such a way that each face is
It's
topologically homomorphic to a disk.
That's too still embedded. I mean, say that.
You don't want some weird embeddings where where faces wind
Then
around.
this one is not out of plan.
Well, so what about trees? Yeah, I'd like trees to be planar.
Embed them on a sphere.
Can you show us a graph that is not outer planar and it's planar?
So the first theorem says that G is outer planar if and only if it does not have K4 or K23 as minors.
So K4, for
So
example.
K4 is not outer planar. So it's planar because this is a planar embedding. And it's not this is not an outer planar embedding because no face contains all the vertices. And similarly for K23. This is a planar embedding, but it's not outer planar. Is that okay?
I managed to guess what Kn is, but Kn comma m.
Oh, sorry. So the complete bipartite graph, we have two sets of vertices, and we put all edges between. So this is K3, and this is K3. And Kn, we have n vertices, and we have one edge joining each pair of vertices.
Why do you define the outer planar? What's the significance to define this to have the outer planar graph?
Well, outer planar graphs are very simple
You see
planar
that it's a
graphs.
cycle, it's one bounded region, right? With one unbounded region, is it right?
Yeah.
So planar,
Yeah, it's also outer planar. You mean that, right?
yeah, I mean, we can assume that all the vertices are on the unbounded region. So an outer planar graph, we have the unbounded region containing all the vertices, and then we have some chords. So this would be a classical representation of an outer planar graph.
Okay. All right, okay, good. Okay.
And then so J is outer planar if it doesn't contain K4 or K2, 3. It's planar if it doesn't contain K5 or K3 as minors. And the Robertson-Seymour theorem tells us that Kuratowski's theorem extends to all surfaces. So for any surface, a graph can be embedded on the surface if and only if it does not contain one of a finite family of minors.
Who's the result on outer planar graphs, right?
I don't know. Does anybody know the outer planar?
I think it's Harari and Chartrand or Chartrand and Harari and Beinecke.
It's very easy because G is outer planar if G plus a vertex is planar. You just add another vertex and connect it to everything else.
Yeah.
And you know Kuratowski's theorem.
But it should be easier to prove than Kuratowski's theorem, okay? Well, Carsten's got a nice proof for Kuratowski's theorem. Here's some more families of graphs. So we have an induced subgraph of a graph is what we get by deleting a set of vertices from the graph. So in well, I guess we don't need an example, huh? A line graph is a graph that we get by, well, I guess it's the incidence graph of the edges of the original graph. So in the line graph, each edge of the original graph is represented by a vertex in the line graph, and two vertices in the line graph are adjacent if and only if the edges are adjacent. So I guess the line graph is going to have 5 vertices, because this thing's got 5 edges. And this edge is going to be joined to everything. This is G, then this is the line graph of J. So we can make line graphs of, here I wanted everything to be simple. We can make line graphs of graphs with loops and multiple edges as well, I guess. Beinecke characterized which graphs are line graphs. So Beinecke showed there's a set of 9 small graphs, each with 4, 5, or 6 vertices, such that a graph is a line graph if and only if it doesn't contain one of this finite family of graphs. And now containment means contains as an induced subgraph. It does not mean as a minor. So again, we can test to see if a graph is a line graph in polynomial time. Claw-free graphs are a more general family than line graphs. So a claw-free graph is a graph which does not contain this graph as an induced subgraph. This is the claw, K1, 3. So I guess this graph is claw 3. And one way to see it's claw 3 is the fact that it's a line graph. So all line graphs are claw 3. K1. This graph is one of Beinecke's excluded induced subgraphs for line graphs. And we'll see later that many of the properties of line graphs extend to claw 3 graphs. So this is my third and final section this morning. So it's probably the most fundamental graph theoretic property, which is connectivity. So a graph is connected if and only if any two vertices are joined by a path. So we would like to measure how connected a graph is. So this is a kind of metric on the connectivity of a graph. So we have the idea of an edge cut. So an edge cut, we divide the vertices into two sets, and we take all edges joining the two sets. So these three edges, E1, E2, E3, would be an edge cut in the graph. So a graph's k-edge connected if every edge cut contains at least k edges. So this graph is, over there is two edge connected. Every edge cut has at least two edges, but it's not three edge connected, because if we take the edge cut consisting of this vertex by itself and the other three vertices, then there are only two edges in that cut. So it's not three edge connected. And the edge connectivity of a graph is the maximum value of k, so that it's k edge connected. So there is edge connectivity is probably more an elementary concept than the vertex counterpart. So vertex connectivity, we're deleting vertices instead of edges. So a vertex cut, I'm not sure this, well, this is the definition we've got. A vertex cut is a set of vertices which disconnects the graph. So this would be an example of a vertex cut. So when we delete these vertices, the graph is no longer connected. And
Dave will probably want you to say that U is not the complete, that U is not all of V.
I don't know, would you, Dave?
I think so.
Well, you say that the empty graph is not connected. Does that mean that it's disconnected?
Well, I think I would rather modify it to say a vertex cut is a set of vertices such that if you delete it, the number of components increases.
Yeah.
That way, the whole set of vertices would never count. But in the final analysis, it doesn't matter.
Good. So I guess I'm assuming my graph is connected. So it's k vertex connected, or I guess graph theorists usually say k connected, if it has at least k plus 1 vertices, and every vertex cut of J contains at least k vertices. So there's a slightly different version of connectivity, which maybe Jeff will speak when he talk about matroids. Yes? Might. So the classical connectivity result is due to Menger. So Menger showed that if we have two vertices in a graph, then the minimum size of an edge cut which separates the vertices is equal to the maximum number of pairwise edge disjoint paths which join the vertices. So this gives a good characterization of, I guess, the minimum size of an edge cut. And similarly, there is the vertex version. So if we want to separate two vertices in a graph by deleting vertices, we really want them not to be adjacent by an edge. So if U and V are not adjacent vertices, then the minimum size of a vertex cut which separates them is equal to the maximum number of pairwise openly disjoint paths which join them. So by openly disjoint, I mean that any two paths in the set have only the vertices U and V in common. So they're all paths joining U and V, so they can't be completely disjoint. They have no vertices in common apart from their n vertices. So well, this is not a particularly good example, but the minimum size of an edge cut separating these two vertices U and V is 3, and the maximum number of pairwise edge disjoint paths joining U and V is 3. Here the minimum size of a vertex cut separating U and V is 3, and the maximum number of pairwise openly disjoint paths joining U and V is 3. So a corollary of this theorem is that it gives us another an alternate characterization of when a graph is k-edge connected or k-vertex connected. So it's k-edge connected if and only if every pair of vertices are joined by k pairwise edge disjoint paths, and it's k-vertex connected if and only if it has at least k plus 1 vertices, and every pair of non-adjacent vertices are joined by k pairwise openly disjoint paths. There is a nice structure theorem for minimum edge cuts in a graph, which is due to Gomery and Yu. So it says basically that we can represent the minimum edge cuts by a tree. And I prepared an example, so it'd be nice to see what it was. Well, it's not a great example. This is my graph, and I guess I want it to be labelled. So let's go T, U, V, W, X, Y, Z. So the Gomery-Yu tree is a tree on the same vertex set as G, and the edges have weights, and we can work out the minimum size of an edge cut separating any two vertices in the original graph by looking at the path in the tree which connects the two vertices and finding the minimum weight of an edge on that path. So an example of a Gomery U tree for this graph would be, well, what would it be?
There must be an algorithm for constructing it.
Yeah. A good algorithm for constructing it. Let's make this 2, 3, 3. Going to be 2, eh? Four. I think that works. So it's not unique, obviously. In fact, it has an addition. So the maximum number of paths, or the minimum size of a cut joining Z and W. We look at the path joining Z and W and take the minimum weight of an edge along the path. So it's either 2 or 2. The minimum size of a cut separating V from X has size 4. So
Bill,
yeah?
can you always guarantee that this Gomery tree is a subgraph?
Yeah, I thought about that like about 3 o'clock in the morning, I think.
I thought the answer was no.
Yeah, my guess would be no, but I couldn't think of an example.
But curious.
No, also, both for Menger's theorem, or at least the edge version of Menger's theorem, and for the Gomery-Hugh theorem, isn't the more natural context to consider a graph with non-negative real numbers on the edges? Or, in other words, the Menger's theorem becomes the max flow min cut theorem.
Well, I think mentioning non-negative real numbers to a graph theorist is not natural by definition.
Okay, non-negative rational numbers?
Well, that's a bit better. But then I would just scale things up so they were integers.
Yeah. Because, and the only reason why
And then I'd replace large integers by multiple edges.
Yeah. Because some of the things that we'll be discussing, in the applications of this to either chromatic polynomials or type polynomials or various things in statistical mechanics, it's often natural to have graphs with non-negative edge weights of some kind.
Yeah. But again, I think we can think of them as being graphs with multiple edges, and so usually. So in fact, the Gomery-Hugh tree has an even nicer property. So if
The weights are not integers.
sorry.
I do not understand these multiple edges because weights are usually non-integer.
No, but so
Well,
I
given
said
context.
I didn't like real numbers, and so Alan said, well, let's use rational numbers. And if I have rational numbers, then for most applications I can scale everything up so that they are integers, and then I can replace integers by parallel edges.
So
I don't know why he conceded to rational.
right. So Bill is the kind of electronic engineer who will build his circuits using only rational resistances.
Only one ohm resistance.
So I think I'm supposed to stop now. Could I have 5 more minutes? So the Gomery-Hugh tree has a stronger property in that. So we said that the maximum number of edge disjoint, or the minimum size of a UY cut is 3. Now if we take, that's a bad example. Let's go TW. So the minimum size of a TW cut is 2. And we do that by finding the path in the tree which joins T and W and look at the minimum weight on the path. But this edge of minimum weight, if we delete it, it divides the vertex set into two pieces. And in fact, those two pieces correspond to the minimum cut in the graph. So the Gomery-U tree, it not only tells you the size of the minimum cut, it tells you what the minimum cut is.
That's a general fact.
Yeah, yeah. It can be found. It can be found to have this property, this stronger
There might
property.
be two tools on that edge.
Yeah, and then I think both of them would correspond
Both
to
of them
minimum
would
cut. So that would be a minimum cut. If we take so this path, then this 2 corresponds to this cut, and this 2 corresponds to this cut.
Yeah, it's
Yeah?
true. If you give any such a tree, you can construct as a graph.
Yeah, because we can use the trick of replacing the edges by multiple edges.
I'm sorry, what was the question?
if you have a weighted tree, can you construct a graph for which that tree is the Gomery-U tree of the graph?
Oh.
So we'd like some kind of structure theorem for vertex connectivity. And such theorems exist, but they don't, only for small values of k. So this is what we do if we want to decompose a connected graph into two connected pieces. So the idea is, oh dear, I knew that would happen sooner or later. Does it still work? In fact, I can't hear it anyway.
We can hear you.
Yeah, you know.
So the idea is we have a connected graph which is not too connected. So we have an idea of a cut vertex. So a cut vertex is a graph whose deletion disconnects this connected graph. So there are two cut vertices, and a graph is non-separable if it does not contain a cut vertex. And a block is a maximal non-separable subgraph. So there are 4 blocks in this graph. And now we can represent the structure of this connected graph, which is not too connected, by giving the block cut vertex tree. So the vertices of the block cut vertex tree are the set of blocks and the set of cut vertices, and the tree is just the incidence between them. So we have B1 and B2, and they both contain X1, and B3 contains X1, and it also contains X2, and B4 contains X2. So this would be the block cut point tree. So there is a similar theory which was developed by Tutt for decomposing a 2 connected graph into 3 connected pieces. And this is it's a lot more complicated actually. So let's look at this two connected graph. Yeah, looks about right. So let's put it down and see if I can get the same answer. So first thing we did over here was we located the cut vertices. So these are the one vertex cut sets. So what we'd like to do is we'd like to locate two vertex cut sets over here, but there are lots of two vertex cut sets, and some of them are not. So the idea is we're going to try and cut it. We're going to try and pull the graph apart along two vertex cuts, but we'd like to try and do it in a unique way. So, for example, this is not a very useful sensible two vertex cut, because if we pull it apart along here, we could also pull it apart along here, and the uniqueness would be gone, because once we pull apart along this two vertex cut, this two vertex cut is going to disappear. So the first thing we do is we locate special two vertex cuts called hinges. So a hinge is a two vertex cut, so that if you look at the bridge, so we delete this two vertex cut and we look at the components, and we look at then we put the vertices back. And we look at the edges, the component plus the edges to the two cut vertices. So when we delete these two cut vertices, we get two components, and it gives us two bridges. And now, if either of these two, if any of the bridges for this two vertex cut are two connected, then we say it is a hinge.
I'm sorry, what do you mean by the bridge?
Sorry, the bridge, I mean the component together with the edges attaching it to the two vertex cut. So this is
prime, right?
This is UV.
And together with those two vertices also.
Yes, and the two vertices. So we look at the pieces of the graph which hang off U and V.
Right.
And if one of those pieces is two connected,
One of them.
yes, then we say it is a hinge. So this two vertex cut is a hinge because this piece on the right hand side is two connected. Whereas this two vertex cut is not a hinge because neither the left hand side piece or the right hand side piece is two connected. So for each hinge, we add a new edge called a virtual edge. So this is a hinge because this side is two connected. This is a hinge. I guess this is a hinge.
The right side is that?
Oh dear.
Give you the point, use the cut point.
Oh, it's true, Carsten.
No, it's not.
Why it is not?
Because there's a
Right
cut
side is not
vertex.
But it's two connected.
The cut point. We chose the middle 2 point. Right side one.
Not a cut.
Yeah, you should have used, instead of V, you should have used the one to the right of,
Yeah.
due east of V, yeah.
Yeah, I don't want to use that one, no.
These two connected, what is the problem?
The W, if you cut it at U and V, then the right-hand piece would have W as a cut vertex.
W?
The 2 pieces, both are not connected.
Yeah, it's right. So add something at the bottom. This rocket needs a base.
Well, I said it was more non-trivial. Help!
That's a trivial XY component.
So what's the problem? You don't want to use UW as a hinge?
Oh no, I do. So this is a hinge.
And is VW also a hinge?
Oh, we want, sorry. Yeah, so there are, yeah, VW is a hinge, and XY is a hinge. So we have XY, UW, VW.
So we should draw this VW virtual edge.
You said you draw the virtual edge. VW.
Yeah, sorry. So is that, I didn't realize that was on the next slide. I think tempus fugit, so I think I'm going to stop here and continue tomorrow. Give me 24 hours to sort it out. Sorry.
Yeah.